In this lesson, we're going to talk about probability. So first, a couple of vocabulary words. The first one is an outcome is the result of an experiment. So an experiment could be anything we do, whether it's rolling a dice, flipping a coin. Those would be experiments. The outcome would be the answer we get. If we flip a coin, we have outcomes that could be heads or tails. If we roll the dice, we could get a 1, 2, 3, 4, 5, or 6. The sample space is the set of all the outcomes. So for example, if I flip a coin, I get heads or tails. That is the sample space. If I roll the dice, I get some number from 1 to 6. That is my sample space. And the probability of an event happening is defined as a success that the event happened over the total. Now, by saying success, we don't necessarily mean it was a good thing. It could be, what's the probability that a car is going to crash? Well, crashing is not a good thing, but in that event, that is the success that we're looking for. So success just means that the event happened. All right, so let's talk about some of these possible questions. The fundamental counting principle works like this. John is trying to select his clothes for work. In his closet, he finds 3 different colors of pants, 8 shirts, and 2 pairs of shoes. Assuming every item will match to the others, how many different outfits does he have to choose from? So we could make a tree diagram to show that he has 3 different pants, 8 shirts, 2 shoes, and find out all of the possibilities. The shortcut to this is if he has 3 different colors of pants, 8 shirts, and 2 pairs of shoes, all we have to do is multiply those together, and he has 48 possible outfits that he could put together, assuming that everything matched the other. Number 2, a typical license plate consists of 3 letters followed by 4 numbers. How many different license plate numbers are possible if letters and numbers can be repeated? So we're saying we have 7 spots to fill. These are all letters, and these are all numbers. So what we do, just like the fundamental counting principle, how many letters are possible? Well, there's 26 letters in the alphabet, assuming we can use them all. And it says I can repeat. So I could use the same letter again and again. So each of these blanks has 26 different values that could fill it. Then we get to the numbers. Now when we talk about digits from 0 to 9, there are actually 10 numbers. And if I'm allowed to repeat, there's 10 ways to fill each spot. So now I multiply those together, and my answer is, let's see, 26 times 26 times 26, 1, 2, 3, 4. Whew, that's a big number. 175,760,000. That's a lot of license plates. The next question says, how many different plates are possible if each letter, that's supposed to say letter, and number can't be repeated? All right, so we've got the same scenario. The first 3 are letters, the last 4 are numbers, but this time we can't repeat. So there's 26 letters I could put in the first blank. But if I can't repeat that, now there's only 25 letters to choose from for the second blank, and then 24 letters to choose from for the third blank. That way we don't repeat any letters. Then we start with our numbers, our digits. There's 10 digits for the first blank. Once we use that one, we can't repeat it, so now there's only 9, then 8, then 7. And we multiply those together. And there are fewer options. $78,624,000. So it just matters if we can repeat or if we can't repeat. So it's important to notice those in the instructions. Now let's talk about independent events. Two events are called independent if the result of the second event is not affected by the result of the first event. So, for example, flipping a coin and rolling the dice. The answer I get rolling the dice has nothing to do with flipping the coin. Those are totally separate. So here's the rule for those. If events are independent, the probability that A and B occur is the probability of A times the probability of B. So here's this one. What's the probability of rolling a 5 on a fair die? When they say fair die, they're just reinforcing the fact that it's not weighted in any way, that every number has an equal chance of being of landing and getting a heads. So let's see. What is the probability of rolling a 5 on your dice? Well, a die has 6 sides. 5 is one of them. So the probability of rolling a 5 is 1 out of 6. What's the probability of getting heads when you flip a coin? Well, there's only 2 sides to a coin, so heads has a probability of 1/2. And according to these are independent events because flipping the coin has nothing to do with rolling the dice. They're not affected by each other. So the answer of this, for the probability of rolling a 5 and getting heads, is 1/12. Occasionally you'll see your probability written as a decimal or as a percent, but a lot of times you'll also see it as a fraction. This one, a drawer contains 3 red paper clips, 4 green paper clips, and 5 blue paper clips. Let's see, how many paper clips do I have here? I think I have 12. One paper clip is taken from the drawer and replaced. So we pulled the paper clip out, looked at it, and we put it back. Another paper clip is taken. What's the probability that the first one is red and the second one is blue? Well, we just said there are 12 paper clips. So what's the probability that the first one is red? There's 3 of them. So I reached in, I pulled out a red paper clip, I looked at it, and I put it back. So how many paper clips are back in the drawer? There are still 12 because I put it back in. What's the probability that the second one is blue? Well, how many blue paper clips are in the drawer? There are 5. So my probability of getting a blue paper clip is 5 out of 12. And we just multiply those, and we can let the calculator simplify if we want to. 3/12 times 5/12. I guess you have to enter the right numbers for this to work. Let's try that again. There we go. 5/48. That is the probability that I draw my 2 paper clips in this way and I get a red and a blue. The first one's red, the second one's blue. All right. Now we look at the next page that talks about events that are dependent on each other. Dependent events. The second event is affected by the result of the first. So a good example of this down here is going to be, I drew a paper clip and didn't put it back. So that's going to change the probability of the second one. And this formula is a little bit confusing, but when we apply it to the questions, it won't feel like it. If the events are dependent, probability of A and B is the probability that A happens times the probability that B happens given that A already happened. So this is a good example of that. A paper clip is drawn and not replaced. What's the probability that the first is red and the second is blue? Well, I already know that the probability of a red was 5/12. Nope, I'm sorry. Red was 3/12. Now the probability that the second one is blue, given that the first one I pulled out was red, works like this. I took this red paper clip and I kept it. How many paper clips are left in my drawer? Now there's 11. How many of them are blue? There are 5. If the question had been that both of them were red, this would have been a 2 over 11, because now that I took a red paper clip, there's only 2 red paper clips left. So the second one was a result of what already happened in the first one. So when I multiply this, I get 3/12 times 5/11, and I did something wrong. There it is. And that gave me 5 over 44. All right. The next definition says 2 events that have no outcomes in common are called mutually exclusive. If event A and event B are mutually exclusive, then the probability of one or the other happening, because if they're mutually exclusive, they can't happen together because they don't have any outcomes in common. The probability of A plus the probability of B. If the events are not mutually exclusive, and I'll show you an example of that one, here's our rule. The probability of A plus the probability of B minus the probability of A and B. So a good example of this would be, say, a deck of cards. What's the probability that I pick a card out of the deck and I pick a 7 and an 11? Well, a 7, or I should say a 7 or an 11. Well, those are mutually exclusive because I can't pull a card that's a 7 and an 11 at the same time. I have to say 7 or 11. This mutually exclusive question, not mutually exclusive, would be something like, I pulled a card out of a deck, what's the probability I picked a 7 or a red card? Because I can pick a 7, a red card, but I can also pick a card that is red and a 7. So I have to do this last piece, and I'll show you how that works as we progress. So a pair of dice is rolled. What's the probability that the sum of the numbers is either 7 or 11? So I'm going to give you an easy chart to help with this. If I roll 2 dice, these are the possible sums that I could get. So we're going to pretend in this instance that one of the dice is red and the other one is green, so that they are distinct from each other, because that helps a lot. So how many possible outcomes, how many outcomes do I have if I roll 2 dice? Well, let's see. There are 36 possibilities when I roll the 2 dice. I could get a 1 and a 1. I could get a 1 and a 2. I could get a 2 and a 2. I could get a 3 and a 1, or a 1 and a 3. So there's all the different ways. So this question asked, what's the probability that I roll a 7 or an 11? Well, since I know I can't roll a 7 and an 11 in the same roll, this fits the mutually exclusive definition. So all I have to do is find the probability of each one and add them together. So the probability of rolling a 7. Out of 36 outcomes, how many of them are 7s? There are six ways I can roll a 7 with my 2 dice. And then what's the probability I roll an 11? There's only 2 ways that could happen. So the probability that I roll a 7 or an 11 would be 8 out of 36, or reduced, I believe you would get 2 over 9. And again, that can be written as a decimal or a percent, depending on what the question was asking for. Now, question 7 is going to give us an example that is not mutually exclusive. A pair of dice is rolled. What's the probability the sum of numbers rolled is either an even number or a multiple of 3? The probability that it's even or a multiple of 3. Well, let's look. Out of our 36 numbers, how many of them are even? Okay, I'm going to go through this whole process, but you could probably guess that there are going to be 18 even numbers out of my 36. So the probability of getting an even number is 18 out of 36. Now, what's the probability I get a multiple of 3? Okay, multiples of 3. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've got 12 of them that are multiples of 3. However, did you notice that some of those numbers just got counted twice? All of these 6s got counted twice, and the 12 got counted twice. So what I'm going to do in my formula, remember how it said minus the probability that it does both? Well, I'm going to subtract the ones that got counted twice. So that was 1, 2, 3, 4, 5, 6. Because 6 of those numbers did both. They were even and they were multiples of 3. So they got counted twice. So we subtract them so they only got counted once. So 18 plus 12 minus 6 is 24 out of 36. And the answer should be 2/3. Okay, so just one more time. Because a number can be even and a multiple of 3, we had some, we'll call it a redundancy. We had repeats. So some of the numbers were in both categories, and we don't want to count them twice. So we subtracted it out so they would each be counted just one time. All right, geometric probability. Geometric probability involves the area. So here's the formula. The area of the shaded region over the total area. Unless, of course, they ask you what's the probability it hits the unshaded region, then that's the success you would put on top. So a dart's thrown at the board and lands on the board. What's the probability it lands in the shaded area? So area of shaded over area of the total. Well, the total is a square, and I know that 10 times 10 is 100. So my denominator here is 100. Now my numerator, how am I going to find the area of the shaded part? I think I'm going to do the square minus the circle. Well, I already know the square is 100. What's the area of the circle? Remember, area of a circle is pi r squared. And in this case, the radius is 5. So that's 25 pi. You can't actually subtract those because of the 25 pi. So we're just going to put this in our calculator. And I'm going to write it in just as it appears right here. Let's see, fraction 100 minus 25 pi over 100. And here's the decimal I get, 0.2146. So I could write it as a decimal, 0.215, or sometimes you might see it as a percent. We've got a 21.5% chance of hitting the shaded region. All right, one more of those. A randomly thrown dart hits this target. This time my target's a trapezoid. What's the probability it hits the shaded region? And the shaded region on the sides, those are just triangles. So I have 2 triangles over the area of the trapezoid. Well, isn't a triangle just 1/2 base times height? So look at your triangle, and both of these triangles are the same because they both have a base of 5, a hypotenuse of 13, but I need the height. So yes, we're going to either need our Pythagorean triple or the Pythagorean theorem to know that 5 squared plus b squared equals 13 squared, and we do end up with 12. So the base is 5, the height is 12, and I have 2 of those, so that's why I did 2 times 1/2 base height. Area of a trapezoid is 1/2 the height, which we found out was 12, times base plus base. Well, if you look carefully at the picture, you should be able to tell that the top is 12 because it's congruent to this middle section. The bottom is going to be 22. And then we're going to calculate these areas to get our probability. So I'm going to do exactly what I did the last time. I'm going to type in just everything I've written here in my fraction and let the calculator do its thing. 2 times 1/2 times 5 times 12 over 1/2 times 12 times 12 plus 22. Now, if you wanted these halves to be regular up and down fractions, you can still use the fraction button, even a fraction within a fraction. It was easier just to write them sideways. And here I get a fraction that says 5 over 17. That came out kind of nice. If I want that as a decimal, I can go math number 2 and say, calculator, will you please change that to a decimal for me? And I get 0.294, which is about 29.4%. And that's how we do that one. So your homework is going to be to practice the section that says probability day 1. So you're going to give that a try, and we can talk about any questions you might have when you finish that. And then we'll pick up on day 2 in the next video.